The purpose of this lecture is to introduce you to a couple of simulations that illustrate a lot of important aspects of projectile motion. And so for this first one, we have two cannons, and they're not very sophisticated cannons, and the simulation as a whole, not phenomenal. But it does illustrate the points that I'm interested in. And so the first thing that you notice is that we do have these two cannons. They have certain speeds there, and if I click appropriately, I can go ahead and change those speeds. I can also, if I click here, I believe, or maybe it's here. Yep, I can raise and lower where this cannon is. So I can see lots of different things occur just by varying a couple of the key things with the simulation. I can also hit the start button, and I can show what I'm showing. It's not entirely clear, but I'll show you what that is because it's pretty nice. And then there's the slow motion, which I'll show you in just a moment as well. So just kind of the default settings here that they start you with. If I can get it to recognize me there. So I'll hit the start button and you'll see the projectiles go. It is not phenomenally fast, but you see that they hit each other. And this is one of the key ideas. So we're aiming these two cannons at each other, and somehow the projectiles that they're launching are hitting each other. The deceptive part about this is that you might think that because this one is aiming up, and you know that the cannon's going to fall, in order to hit the cannonball that this one fires, it's going to have to aim upwards even more. That's not the case. And the reason is because this one is also aiming its cannonball at this cannon. And you might think once again, well, this one has to overshoot, right? Because it's up here, sure, that gives it some height, but the projectile is going to fall. So in order for the projectiles to intercept each other, all they have to do is aim at each other because both projectiles are going to be influenced by gravity. And here's the part that I like. If I hit the show button, then what I can do is when I start, you'll notice that there's a line, a vertical line for each one. And this vertical line shows us the displacement from the straight line that's connecting the 2 points. And you'll notice that both cannonballs have the exact same displacement from that line connecting them at every single point in time. Hopefully you can deduce the reason for this. It's because of gravity. Gravity is affecting each one equally. It's causing the same acceleration vertically downward in each case. What that means is that as long as gravity is acting on both objects for the same amount of time, it's going to cause the same deviation from the non-gravity path. So if there was no gravity, it's pretty easy to imagine that these two cannonballs, if you aim them at each other, if you aim the cannons at each other, the two cannonballs will collide with each other with no gravity. You know, they're just going to go along this path and hit somewhere in the middle. With gravity, however, we know that that's not true. They're not going to go right along the path. But what they do is they deviate equal amounts from that vertical path. And it's not just this one case that it does that for. Let's say I make this one faster. You see that there's less deviation from the vertical path, and that makes perfect sense because it takes less time for the collision to occur. This one's traveling faster, so it moves greater than half of the distance, and as a result they collide in much less time. So the deviation from the non-gravitational path is exactly the same for each of these cannonballs, but it's less than what it was before because they're going so much faster. And if I make them slower, which we can do, they may not actually hit each other. It looks like they will. And here, because this was going slower, we get a much greater deviation from the non-gravitational path because it takes longer for them to intersect. Let's just show this one in slow motion there, so you can see the dramatic effect of the slow motion. That's too much. I can't wait that long. So, slow motion, kind of boring, but the rest of it at least gives you the idea of what's taking place, what's going on. And we can do things like vary the the height. And you can see that even though they didn't collide with each other here, they did have the same deviation from the vertical path. So anyway, that's the first one. Okay. This simulation actually has two parts. There's case 1 and case 2. And I'll show you case 2 to start with. Case 2 is really just illustrating a lot of the same ideas. We have this projectile. It's initially launched entirely horizontally. So it's going to take this sort of curved parabolic path that you see laid out. But in addition, there's blocks at each of these locations. And what's going to happen is all of these blocks are going to be released at the exact same time that this is fired horizontally. And what we're going to see is that it intersects every single one of them. And this just goes to show once again that the horizontal and vertical components are independent of each other. These things were all in free fall the entire time. This one too was in free fall the entire time. And so they deviated from the non-gravitational path, which in this case was this horizontal path, by the exact same amounts. Now we can change a lot of different things here. We can make it, for instance, go faster. And that's not terribly dramatic. It's just going a little bit faster. So everything's been spaced to account for that. What I think is a little bit more interesting is if we give it an angle. Oops, gotta reset it. So if I give it an angle, you'll see that we're now directing it up along that angle. That's the main idea here. And each of these is the same length that it was before. Each of these bars is the same vertical length as it was before. And when I let it go, you'll see that we're continuing to hit every single one of them, because all of their deviations from the non-gravitational paths are identical. This particular object right here, for instance, without gravity, it would just stay there, as with this one, as with this one, as with this one. And this particle that we fire would just go right along that straight line path if there was no gravity. Well, with the presence of gravity, it doesn't matter that these ones are starting at rest and this one's being launched upwards at an angle. Because they're both being influenced by gravity, or I should say they're all being influenced by gravity equally, they all deviate from the non-gravitational path by equal amounts. And this last one is just kind of neat. You can set the speed of it, and you can set how many projectiles you're going to fire, and you can fire them off. And one of the great things about this is that it shows, first of all, that the ones that you fire straight up are going to take longer to get back to the ground. And you can see that these ones, this one that went vertically upward, this marks its maximum height. So this is the maximum height that any projectile can get to. If you look at these other ones, they're less high, but it's still marking their highest point along the path. Okay, and so you get your ones here that are going completely horizontally at the time that they get there. Well, actually, they're all going horizontally at the time that they get there. But this one's looking, what I meant to say was about 45-degree angle. And then you get your ones that are not angled up so high, and they're encountering this much sooner because they're not going up very much. It doesn't take them long to turn around and come back down. The other thing that you'll see is that there are intersections between projectiles launched at different angles. So this one here looks like it was launched at about a 5-degree angle, let's say, maybe 10 degrees, and this one launched at 80 degrees. So one launched at 10 degrees and one launched at 80 degrees will go the exact same distance if we're firing them along level ground. And we'll say this one's at 70 degrees, that'll encounter one that was launched at 20 degrees. This one, obviously, at 70 degrees takes a little longer to get here than the one launched at 20 degrees, but they will eventually get to the same point along the ground. And you can do some other things here, and you can play with them on your own. You can make this, let's say, 50, but we'll make it a count of, say, 80, and we'll reset it. And you'll see everything got squished in quite a bit more. It's not going to go nearly so high, but we have a lot of them to look at. And we get that very neat, interesting arcing pattern. And you can't see as much detail here. It just looks kind of neat. So you can play around with this. You can play around with the other one. And hopefully you'll get the idea of the independence of the two directions of motion, and also the interesting properties that arise based on the angle of launch and the complementariness of certain angles, for instance 80 and 10, 50 and 40. And that also leads us to an understanding, hopefully, that 45 degrees in the absence of air resistance will get us our maximum displacement. That's the one that passes right through this part of the ellipse.